Okay. My name is Gavin Nielsen. So day 9 of 11 now instead of 12, and this is going to be cool. So this is all about physical modeling. We're going to get into any domain we want to get into, and we can create our own domains, and it's going to be kind of neat. So, right. So we've finished our basic stuff. We've done some algorithm modeling. We did geometric modeling last time, and now into physical modeling. And so here is what we're going to cover. Won't be exactly in this order, and we're actually going to put off the project work just because there's so much. There's just a lot of concept stuff. Like we'll be working inside Simulink and Simscape, but I think it's just too much to fit into today to do all the concept stuff and actually get to the project work. So we'll build a bunch of hydraulic circuits and that kind of stuff, and just kind of get a feel for it and break some stuff. So we're not really going to get much in the way of project work done, but next time we'll connect our geometric models up to the system models and electrical models, and once you feel comfortable, it won't be too bad. So, domain-specific abstractions. We've been talking, I mean, that's modeling 101, right? Abstract yourself from the reality and make something mathematical or make something geometric or whatever. So why do we need yet more? Why domain-specific? Well, state machines, I think, are a really good example of this, because remember how much easier it was to model the bouncing ball with a state machine? It was so easy because it was a really good fit. It made a whole bunch of the right notional assumptions for the bouncing ball. So it was really easy to model the bouncing ball. I can't remember. It was like 6 lines or 10 lines of code or something, right? And have you guys already seen Z transforms and Laplace transforms? I'm sure. Yeah. And those are a certain type of domain-specific, time domain-specific abstractions of, okay, assume that blah, blah, blah. Assume that you're at a discrete sampling time, and that's the Z domain. Assume that you have a continuous sampling time, and that's the S domain. So why keep adding more? What's, isn't enough? Like, well, there's more than we're going to cover just because of the variety in the world, right? But the main reasons we want to keep adding more are the same things we've been talking about, like speed of development, simplicity of representation. We want to be able to leverage the implicit notions of whatever kind of space we're in. And then this is really key for today. It's funny, the more detailed and the more abstract you get, it looks less and less like the thing you want it to look like. It starts to look like equations or weird looking, block diagrams with feedback loops and gains, which looks nothing like a circuit or a turret. So another reason that we'd abstract ourselves, it's kind of ironic if you think about this, is we abstract ourselves away to get closer back to reality, so it doesn't feel so foreign. And you'll see what I mean here in just a little bit. Sometimes those more foreign things, like having equations or block diagrams, tend to be kind of brittle, and where you make a change, and a little change ends up being like you've got to rewrite 30 equations, and that's really not efficient, and it's really error prone. So I really liked the video introduction that they have. It's like 2.5 minutes, and they kind of go through a whole bunch of things and explain about Simscape. Why not just, this is from the MathWorks, why not just use Simulink? That's another one of their products. This is explaining why they built it and what it's useful for, so I'm going to click on this and I'll turn up the volume.
Simscape enables you to rapidly create models of physical systems within the Simulink environment. You model systems such as electric motors, bridge rectifiers, hydraulic actuators, and refrigeration systems by assembling fundamental components into a schematic. The models you create can be placed in subsystems so that you can reuse them in other models. The models you build are based on physical connections. To model a mass spring damper, you simply connect mass, spring, and damper components, and Simscape determines the system-level equations for you. This is much easier than deriving the equations and implementing them in code or by connecting input-output blocks. As the system becomes more complex, the modeling method enabled by Simscape becomes even more powerful. Extending the model is as easy as copy and paste. You can create custom components using the MATLAB-based Simscape language. You can take the code we provide and modify it to include the effects you need for your design. You can integrate electrical, hydraulic, pneumatic, and other physical systems into your model using the components from the Simscape family of products. Simscape offers a set of fundamental components in many physical domains, and it provides the technology for simulating and analyzing physical systems. The Simscape add-on products provide additional models and analysis capabilities for applications such as electric power networks, heating and cooling systems, and mechatronics. You can integrate these with three-dimensional mechanical systems and analyze their behavior using an animation of the simulation results. Simscape models can also be converted to C code. This enables them to support testing of embedded software in configurations such as processor-in-the-loop and hardware-in-the-loop testing, which is much safer and more efficient than testing on hardware prototypes. Simscape models integrate directly with block diagrams in Simulink, state machines in Stateflow, and MATLAB functions. You can simulate your entire system in a single environment. This accelerates tasks like designing control systems and optimizing system-level performance.
Okay. That was pretty direct and to the point. Had a lot of good visuals. So one of the main differences between Simulink and Simscape, and you make a Simscape model within a Simulink document, right? Is the fact that if you look here on the left-hand side, all the information flow has arrows, so it's going from here to here, so it's unidirectional. In Simscape, everything's bidirectional, and if you think about how reality works, it's bidirectional. Like I push on this TV and it pushes back, and so I can't get away really from the bidirectional thing. That's why whenever you go model a physical whatever, there's feedback loops. But it's hard to visualize the feedback loop, so it's really nice to implicitly say, I'm going to connect this resistor to this voltage source, and it will push and pull, you know? It will push voltage and pull current. So that's one of the biggest differences. So let's jump in and not talk too much before we get dirty with this. Let's see. Any questions? I'm just going to keep cranking.
Is Simscape something that comes standard, or that comes with MATLAB, or you have to download that separately? Pay for it?
I don't know about the student. Is it you have to pay for it separately? Yeah. Okay.
Yeah. If you call them and you ask very nicely, they can discount it to $10 for you potentially. I think Simscape's multiple packages, right? There's different Simscape packages.
Yeah. There's a base and then some. It's an add-in to an add-in to an add-in, you know, but it has specialized domain stuff.
Oh my gosh, $2,000. Yeah, that's why you don't want to go and get jobs.
Oh, there you go.
Stay in school.
Yeah, there's a student one. There's a student one.
Stay in school, man.
Stay in school forever. Special student.
Yeah. Okay. So, all right. So let's do this. Make a Simulink model. So while that's kind of booting up, come on, get out of the way. So this, no real big mystery here, right? It's a voltage divider network, 12 volts DC goes through two 1K resistors in series. We all know how that works. One thing that's kind of different than the other, like Stateflow or vanilla Simulink, is that you have to attach a solver configuration block to all the networks. And at first it seems like, man, another thing to do, because you have to attach grounds, and you really have to form a circuit. You can't leave ends just hanging. But the reason is because like having a local solver gives you the capability to say, this electrical network needs to solve maybe with a time constant of something like, I don't know, 10,000 or 1 millionth of a second, where you would be wasting a whole bunch of time if you had to solve mechanical networks that fast, because their time constants aren't nearly so small. So that's one of the side benefits. So now we've got this. I'll get a blank model up here. I'll kind of demonstrate how to build this little guy. Have any of you guys used this before, Simscape? No?
Not Simscape, no.
Okay. So I'll click on the library. Do any of you have it now with you? You do?
Do you want to share with me, Benny?
What's that?
You want to share with me?
Sure.
Okay. So when you have it installed, are you looking at 16A or 16B?
B.
B, okay. Yeah, way advanced. So here's the Simscape. Remember up here was the regular Simulink stuff. These are all different add-in stuff. Simscape is another place, and you can look in the foundation library for all the basics. So we'll go into the foundation library, into the electrical domain, and electrical elements. And here it has all of the stuff you'd expect, grounds and diodes and capacitors and all that kind of stuff. So I just dragged and dropped, but it has to load some stuff when I drag and drop, so okay. Alright, and I'm gonna just rename this.
Have you actually tried comparing any of the behavior of circuits that you're making this with, let's say, SPICE? Is it like reasonably accurate as far as modeling physical devices?
Yeah. I did a project, one of the side projects when I was working on my thesis, and I did an optical voltage isolator, so that you could have voltage swings that were the same size but at different absolute offsets. And they had SPICE models available, and you can actually import SPICE models into Simscape. It's not a perfect translation, so you usually have to tweak something or other, and they're talking about, or they've been threatening, I guess you'd say, that we're not going to support this forever. But thus far, it's still worked to import SPICE models.
So you can import SPICE models into Simscape?
Yeah.
Wow.
Yeah. So yeah, it's been pretty good. And one of the things, when you do SPICE simulation, how you can do a DC analysis or a frequency analysis or that sort of thing. And you kind of have to keep in mind that, for better or for worse, Simulink thinks in time. So if you're going to do like a frequency analysis, you can extract a linear operating point, or identify a model, or actually do a time simulation of a frequency sweep, but it's not quite the same thing. And that, on the one hand, you think, man, it would be easy if I could just do a frequency sweep. But one of the nice things is you can do stuff in time that you can't do in the frequency domain. And so you can keep those effects present and do your frequency sweep. You just have to do it in time. Does that make sense?
Yeah.
So I mean, it seems to me pretty accurate. I wish I had I thought about it today. I had an actual and predicted, and they were very close. What I predicted the performance was going to be, of my voltage isolator circuit, as far as frequency response goes. But yeah. Okay, so one of the things that almost all of them are separated, they have elements, sensors, and sources. So we're going to add some sources here, and we'll put a DC voltage source, connect the dots, and then we'll go back to elements and put in a couple of resistors.
When you were typing, a question, when you're typing in, let's say, voltage source or whatever, is there any way so that the list that pops up is restricted to, for example, Simscape?
Not that I'm aware of. But one thing they changed, I don't know, a release or two ago, was that you don't have to type the words in the order that they appear that you're looking for them. So like, yeah, you could type in source, voltage, or voltage. You don't have to type in DC, because you get all kinds of things, you know, if you're just typing in source, for example. So that's helpful, but it doesn't exactly limit. It just has to do with the naming conventions. So here's our little circuit, and this is complete in form, but we need to add a couple of things. So we need a local solver. I guess they call it a solver configuration.
Another question. You chose a DC voltage source, and I noticed that was listed under the SPICE compatible components. There's another component, at least for me, that is just called voltage source. I don't know. Do you know if there's a difference between the two?
Well, there's probably a difference. I don't know what the difference is, to be honest. Yeah, I'm sure it's got something in the doc files about it, but okay. So this is Simscape, now that we've abstracted ourselves from the details of how a resistor works, that model has been built for us. We have to double click on the model and put in the parameters that they parameterized it with. And so we'll make it 1 kilo ohm. So value and unit. That's another thing that's really important in Simscape, is that it cares about units. It's not just 1,000. You know, it doesn't imply or we'll talk more about that in a second. But the units are important, which is nice actually, because that means you can specify one thing in one unit and ask the question in another unit, which, depending on what you're doing, is really helpful. Maybe, you know, your data sheets in SI units, and you'd like to know in, you know, imperial units or something like that, because I don't think in meters. I think in inches, feet. So anyhow, so I'll make it 12 volts. Okay, so I'll hit go, and it automatically compiles, figures out a good solver to use, and great. But one of the issues here is the fact that we don't know what it did. Like, there's no place to hook up a little display on there. We can't really drive it with anything. So we say, well, it's a voltage divider network. I know how that works. But then why the heck are we modeling this? we need to. There's a reason we want to learn how this works, right? So before we get into the sensors and actuators and sources and stuff, let's just talk about the implicit feedback loops. So if we look at this, we don't have any loops here. I mean, even topologically, we don't have any loops. I guess we have an implied node that's the same. So we have one loop because it's a circuit, but we were just talking about before you came in that these signals are bidirectional, right? So this can push and pull energy and information, whereas like a Simulink block diagram has arrows, and it's going from here to here. And one of the things about that's really an important concept from a modeling standpoint is the fact that the feedback loop is implied, that you can push and pull, both affect and be affected, because that's the way reality works, like for physical systems at least. So the reason for that is because if there wasn't any feedback, there wouldn't be any energy balance in the system. So I could push as hard as I wanted, like let's just say that I'm a block and my block has something to do with velocity, and I don't care if you weigh 100 pounds or 1,000 pounds, I can just push you at this speed. If I don't have any feedback, that means I really it's not very accurate to reality because it takes a lot more force if you weigh 100 pounds or 1,000 pounds. So that notion of having implied feedback loops or having a bidirectional information flow makes every physical system a type of control system, which is why I really enjoy control system design, because it's a really useful way to think about the world in general. Even if there's like no active controller, and I picked this chair up, well, how am I holding this up? I mean, if I close my eyes and try to hold my arm still, like my muscles are tense up here, and if I had no feedback, like they would just continue up. But the fact that I have physical feedback and the tension of the muscle, I have electrical feedback and my senses, all that kind of stuff, makes any physical system like a bridge. Think about the stability of a bridge and the stresses and strains that hold it there, and gravity holds it down, right? And the design of the bridge holds it up. Like those implicit feedback loops actually hold it from just flying apart. And so that was one of the things that for me was like, everything's control systems. That's awesome. You know, like now I have one way to think about that. So if I can convince you guys to get control systems, I'll try. So think about like in electrical circuits, a voltage source doesn't act without some way of thinking about its load. If you have a higher resistance load, then you can't push as much current through it. So I try to push, I have this voltage present, this energy, this potential energy, and it's not without regard to you. Say, Gary, you're a resistor, and I'm voltage source, a battery, and I'm pushing current through. Well, you're implicitly telling me I will impede your flow by this much, and I'm saying, but I've got all this potential energy, and you're saying, not through me, you know what I mean? Like there's this back and forth, and that's the way every physical system works, which is why, you guys know a lot about circuit analysis, which is awesome, because what we're going to see is that there's a mirror, like an analog, like a Rosetta Stone between electrical domains and hydraulic domains and mechanical domains, and you can make circuits out of all of them, which is really, really cool. Another thing you can think about is Newton's third law: for every action, there's an equal and opposite reaction. It's just saying that it goes both ways, or think about the fact that you're trading kinetic energy and potential energy back and forth. Those transactions in energy are bidirectional. So anyway, not to beat a dead horse, but that's really important. All right, so now any questions about that before we move forward? Yeah.
Could you explain again the purpose of the solver configuration? Why it freaks out when it doesn't have that included in the circuit?
Yeah. There are some, let me show you. There are some things about the solver configuration that Simulink needs to know no matter what, even if you're not using the local solver. Like here it's unchecked, so we're using a global solver, and we'll see more about this later. Even if we're using the global solver, not this local solver, there are still details that you need to specify. Like for example, do we apply filtering or not? And that kind of stuff. So I'm sure there's more under the hood that Simscape is just handling for us because it's attached to a local solver, but I don't know all the details, and that's kind of the point in a way. Like, I don't want to know the details. They haven't told me the details.
I just find it kind of odd where I have something that I'm not necessarily at least directly using, but when I try to simulate the circuit without the solver, it yells at me and says, you gotta have a solver.
Right.
And I'm thinking, well, what's the reason for me to need the solver if it's, I guess, to load some sort of values or some sort of parameters that you should have at least assumed?
Well, so just as an example, this is a good one because, you're either applying filtering or you're not, right? So if you don't have something connected to tell it, apply filtering or not, what does it assume?
Some sort of global parameter, I would imagine.
So that kind of comes down to the architecture of the software of how they designed it.
Yeah,
you know,
okay.
yeah, I can't defend because I wasn't part of that team, you know, but that's what it boils down to.
Yeah.
But I think you'll find once you start using it, it really helps because, like I was saying a little bit ago, different physical systems, like you might have an electrical system that's really slow. You know, it has like RLC time constants that are big. Maybe it's some power circuit, and it just doesn't move that fast. You don't want to solve that at a microsecond scale. It's so time consuming. I mean, there's all these data points that are just useless. Whereas some other microelectronics signal thing, you've got to solve it at like nanoseconds because that's how fast stuff's switching. So this local solver gives you the ability to put those two things together and do some signal level stuff next to some power level stuff. So.
What does that filtering time constant exactly mean? Like if you were to change it from 1/1000th to like 5, what does it change in how you see the circuit or how it solves it?
I'm going to defer that because we're going to talk about it. So just hold on to that. Okay, good question. We will talk about it in just a second. So I'm going to call this, I'll call this basic 1. All right, so we were just talking about the fact that we're solving this circuit, but we don't know how to get anything in or out of it, right? That was our next direction. So the way you get stuff in and out, and at first it's kind of like, man, like we have to literally add sensors and literally add drivers. But what you get is a bridge. You get a bridge over to Simulink and to other domains. And so we'll build this real quick, but I'll walk through what it is. So here's our solver configuration. Here's our 1K resistor network, just like it was before. And we're replacing that constant DC voltage with a controlled voltage source. And then there's this translator block, Simulink to PS, which stands for physical signal converter. And so you'll see there's a directed signal coming in the left-hand side, and I guess you'd call it a semi-directed signal. It's a different kind of directed signal, and they call it a physical signal. So it's not actually bidirectional, but it has like half of the stuff. Like it has the units and it has magnitude. It just doesn't go bidirectionally. So we'll talk more about that in just a second. So here's the actuator part, and then the sensor part is literally a voltage sensor. And just like in reality, you have to measure across, right, for voltage in parallel. So you connect the nodes across, and then the output is the voltage that goes through another, this time in the opposite direction, from physical signals to Simulink. And so you could put in volts over here and pull out millivolts over here, or some other unit. And then you can put that into any of the other Simulink stuff that we know and love, right? Like scopes and displays. So let's build that real quick. So.
81, holy shit.
Huh?
Oh,
What?
the number of alerts.
Oh. Stop reading my. Glad I don't have my email open. You'd be reading that too. That's funny. I should mention, on a personal note, the reason I was late today was because I was busy getting a ticket.
Oh.
Yeah. So that's why I texted you, because I was like,
shit.
crap.
Sorry.
I'm late. Yeah.
Fight it.
Well,
Make the cop work for it anyway. It doesn't matter if you deserve it.
I deserve it.
Yeah, but
I'm
people
like
did deserve it.
a year late on my registration, so I deserve it.
Oh,
But
okay. So it was the speeding.
no.
Oh, okay, no, yeah.
Yeah. And he could have towed me. So he didn't tow me. I was like, thank you. I really need to get to a seminar. So, yeah. Okay, so I just pulled in this controlled voltage source, and if you double click on it, you can't do anything. You can see the source code if you want to, which is interesting, but not what I want to do right now. So this it just has one physical signal input port, and then two physical output ports. So what I need then is, if you go down to utilities, there it is, we need to go from Simulink to physical signal and then connect them. And you'll notice they're different colors. This is blue and this is like a pinkish color. Every domain is different, so when you look at it, you can see, oh, this is blue and this is brown or this is green or whatever. And that way you realize, like, you can't connect an electrical circuit to a hydraulic circuit. That doesn't make any sense. And so you can visually kind of see that. Okay, so we need a manual switch. Come on. To feed in there. And we'll put a constant. And we'll put a step function. Speaking of feedback, it's interesting that how motivating getting a ticket is to fix stuff, though. Negative feedback. So the final value, we'll start it at 6 volts and go to 12 volts. Oops, step time. Initial 6 volts. Okay, and now we'll pull up the sensor stuff again. So electrical sensors. There's voltage and current. So we'll drag the voltage sensor here. And you don't have to do this, but it's nice to get it flipped around so it's the right way. So we'll just flip it left, right. Okay, and then we need to go the other direction, right, from physical signal to Simulink. So I'll just type in PS, is it dash? Yeah. So Simulink. And put a display. Put a scope. Okay, and I'll make this 12 to start with. So what should happen? I mean, what should go on the display when I do this? If I have 12 manual switches connected, I'm controlling this voltage source. We set these to 1K each, 1 kilo ohm and 1 kilo ohm. So I'm making a voltage divider network. It should be, you should do this in your sleep. What's the voltage right at this node? This is 12. It's going to be 6. So it's nice to have some kind of a expectation of what should happen so that when you run it, you can say, does that seem reasonable? So we'll run it real quickly. 6, okay. Not super exciting to look at on the scope because it's just one value. Come on, 6 volts. Okay, so let's switch the manual switch over to use the step function. Oh, yeah. So that's 6, but we should have a step up from 3 to 6, right? Because this went from 6 to 12. So that looks good. So we did some time domain stuff there. Any questions about that? So, yeah, it's not new theory. It's just how to do it in Simscape, right? Okay. So we already talked about the coloration. This is an actuator or a source. Yeah.
I really think that control voltage source, is that like if you wanted to put a sine wave on it, can you just kind of use it for AC, or is that like strictly for DC signal?
No, you can do anything you want. Yeah, you can put a sine wave on it, or yeah. Okay. Any other questions before we're just gonna keep cranking? So the next thing, we didn't really set our units. Voltage is kind of the default unit, so when we leave the input signal unit as 1, it just assumes, okay, I guess you mean whatever the default is. But let's just look at it real quick. So if I double click on this, it gives me, okay, what would you like to use? So here's some of the units. and this doesn't make any sense, right? To put in radians per second into a voltage source. And so let's just do that real quick. Say OK, and run it. Okay, invalid unit specified. So it checks you. It's like, does this make any sense? So it has to be commensurate. You have to be dimensionally the same. But you can also, maybe we want to talk about millivolts, MV, and then this should come out 0.006. So that makes sense. Pretty straightforward. Okay, so sometimes this was just added actually in 2016A. Simulink actually can display units much in the same way it can display dimensions of, like, whether there's a vector signal or a matrix signal, whether a signal is a vector or a matrix. So let me show you how that works real quickly. You go to display on the menu, go to signals and ports, and click on port units. So this has millivolts, and this has 1. The 1 is just because we didn't specify anything. So if we change it to volts, then this switches to volts. So now when I run this, nothing should change. But within Simulink, it understands that on that signal, even though it's just a mathematical quantity, and it's still unidirectional, it has a unit. And that's actually super useful because it helps you check your own assumptions in whatever's on the Simulink side. Does that make sense? Okay. So I have a sneaking suspicion this is completely reviewed for you guys, but it's worth saying something about because of the fact of this is what we're talking about today. But quantities, dimensions, and units. So in Simulink, we've really just been throwing quantities around. We haven't really talked about units. And not if this is review, like there really only are a few fundamental units, or I should say fundamental dimensions, and then there's a whole bunch of different units and combinations of things. So velocity isn't its own dimension, it's a length per time dimension, and so it's a derived dimension. This is not new, right? This is old stuff, right? Okay. And so we can specify our units in these different symbols, but we're really still working with, is it a temperature, is it a length, is it a volume, length squared, length cubed, stuff like that. So I'm not going to dwell more on this, but this is useful to remember. Like, dimension is such an overloaded thing. How many different ways have we talked about dimensions this semester in the seminar? I think 3 different ways already. Dimension of the size of a matrix, and the dimension of what the space we're working in geometrically, and the dimension of, now it's what's the fundamental dimensions in physics. So it's definitely an overloaded word, but it's useful just to think about the fact that, for example, frequency is not a fundamental thing. It's just a way of thinking about time, and it's 1 over time, or that's the idea. That's the fundamental dimension of it. Okay. So within Simulink, like I said, this is I've just been playing with this recently. It's super cool, actually. Not just on a nerdy level, or geeky level, whatever, Tony. But it's actually super useful. It's super useful because thinking about it in terms, like, you're making some block diagram, right? And we're focusing this tonight on physical modeling, but you're going to have bridges back to Simulink so that you can put stuff in and pull stuff out of your physical model. So understanding and making sure that your units are reconciled on the Simulink side as well as on the physical side, on the Simscape side, is really important. So I thought it was worthwhile to look at this quickly. So I showed you this before in the display menu, on the signals and ports submenu. You can click on the port units, and then it shows you, okay, this is where it is. And if we look back at our model, this Simulink to PS converter is where we put the units in, it implied that that means that the signal coming into it was of that unit. But these over here on the input to the switch don't have the same implication. Seems like with the switch, in my opinion, that maybe should have propagated, but I guess MathWorks didn't think so. So who am I to argue? But seems like it would be something you might want to do. Anyway, but there's some interesting kinds of rules for this. So there's back propagation, which is what we just saw. And if you use a block called signal specification, you can say, I'm working in this unit. Like in here, I'm using kilograms. And so it implied that backwards, coming into that, you must be talking about kilograms coming in because you're specifying this signal is of kilogram type, or kilogram unit. And of course, it makes sense that right after you make that specification, it's going to have the kilogram. But then you go through something that modifies the signal and gives it a different output from that input, like a gain block, and there's not the same signal spec there. So it's just something to keep in mind when you're building in, your sophisticated Simulink model, how the units work. It's nice to be able to turn them on and see where they propagate to, and that way when you're doing some math, it really forces you to say, okay, what units am I in now? Does my math make sense? If I'm in meters per second and I multiply by seconds, I should have the dimension meter. And then you specify, okay, so the output of this is going to be in meters. But the math may not have all of those signal specs on it in the intermediate steps. So there's some neat unit converters, and it's called the unit conversion block, and gives you some feedback that you can see without even running the model, which is pretty handy. So here I have 1 kilogram, and I specify it with a signal spec block. And so the input and the output of that is kilograms. And right here, I just drop a unit conversion block on. And then right after that, I say, my new spec is in pounds mass. And lo and behold, it does the conversion for me, which is pretty handy. Because I don't think in kilograms, I think in pounds mass. But you can't just drop a signal spec right after a signal spec. It doesn't, and so it has this little symbol here that there's no automatic conversion happening. So 1 kilogram is not 1 pound mass. By the same token, you can't mismatch units. So I tried to convert from kilograms to hertz, which doesn't make any sense. And so it has this little red triangle thing saying that. I don't know what to do with that. So anyway, this is just a little about, and you can't do it implicitly, and you can't do it explicitly with a unit converter because neither one makes any sense. So yeah.
So in this case, let's say on the very top, you're converting the number 1 in a unitless quantity into kilograms, giving it the dimension of kilograms.
Right.
So
the unit.
Sorry.
The unit of kilograms.
Yeah. The unit of kilograms. So when you go down 1, what that is telling MATLAB is saying, okay, I want to convert this 1 kilogram into 1 pound mass, because it still has that number associated with it. It's not actually doing a conversion in terms of the ratios of their quantities. It's just reassigning the unit of that 1. That's why you have 1.
The second line down?
Yeah.
Well, part of the problem there is that it has that back propagation and forward propagation, and these share the same node.
Mm-hmm.
So it doesn't really know what to do with that.
But it's displaying 1.
Well, it failed to do any conversions, so 1 kilogram came in, and if it was correct, it should say 2.205, but it says 1 pound mass out.
Okay.
Do you follow what I'm saying? So this gives us a warning, some feedback to say that this isn't going to work. This isn't working the way you think it is.
Right. It's not converting kilograms into pound mass in the conventional sense that we would. It's just converting that unit that's appended at the end.
Yeah.
So
It's changing the spec,
Yes.
but it's telling you that it's not doing it right.
Right.
Yes. Okay. So this is straightforward, and I'm not going to say any more about it if you guys don't have any more questions. You good? Okay. All right, so now we get to something a little different, a mechanical circuit. So stare at this for a second, and does this, I'll walk you through what this does. It's a very small network. There's a velocity source, a mechanical velocity source. So I'm telling this thing to go a certain speed, and the only other part of this is there's a mass. Well, I suppose there's a translational reference, which is kind of the mechanical equivalent of the ground. And I'm saying, go this fast to this inertial mass. And then I give it a step input. So it happens that it's going from 0 meters per second to 1 meter per second. And so just think about this for a moment. In time, at time equals 0 to time equals 1, this isn't moving. And then right after time equals 1, this is going 1 meter per second. That's what this circuit does. So how much force should this take? Like, you can guess or you can just talk about it qualitatively, but when you look at this and you're going from 0 to 1 with a step function, yeah, like if it really followed the rules, right? Because that step function goes directly to 1, and it's driving this mass.
The acceleration is the slope of that.
Right. Right, and so the derivative's infinite, right? Okay. So the analogy here is a voltage source creating a current in an inductor. You can't just do it like that fast. It takes a little bit of time and to get going. So let's build this real quick and try it out. Solver. We need a translational reference. We need a velocity source. We need what else was there? There's a mass. We need a motion, translational motion sensor. We need a force sensor. Okay. We'll need a PS to Simulink, and we'll need a Simulink to PS. Turn on our units. Port units. Okay. So I'm going quick because this is boring to watch if I don't go quick. This one goes over here, and this one goes over here. So I connect up the physical signal, and I'm going to drive it in meters per second. Okay. And I will, I need a step function. Right, so it's meters per second, so that's good. I'll connect the ground. I'll connect the mass. Connect the solver. Solver just has to be connected somewhere. It doesn't really matter. It just kind of needs to be connected at any point in the circuit. All right, so two things. We'll talk more about this in a little bit, but there's a cross, and you guys already know this. This isn't something new. It's just a new way of thinking about what you already know. There's across variables and there's through variables. There's serial types of things and there's parallel types of things. And so in electrical world, what's the through variable? Everyone together. Current is the through variable, right? You have to put it in series. You know this, I know you know this. And voltage is, of course, the across variable you can do in parallel, and that's why we hardly ever measure current, right? Because you have to mess with the circuit. Well, in the mechanical domain, force is the through variable, so we have to connect it in series. And velocity is the across variable. And so we also have to give it a reference, just like we'd say, how fast are you going with reference to what? So if you have relative motion, you can talk about it, just like we can talk about relative voltages. But we're talking about it with reference to ground, so we'll connect it to ground. And then we can look at velocity or position. We don't really care about position, so we just want to look at velocity. And we'll use the output unit of meters per second. Okay. And this is going to be an LBF, pounds force. Alright, I'll put a scope on here. I usually hide most of these words. I'm just leaving them because when you haven't made these before, it's easier to see what's going on. Like, see the names of things. But it, you know, generally good practice to not have all this stuff in here because it doesn't help you much. It just makes it look messy. Especially the grounds. I think I'll hide those because they're just annoying to me. Okay. Alrighty. So let's run this quickly and look at our. So this is, remember, this is the motion sensor, and we're looking at the velocity. And so since we're controlling the velocity, we know exactly what we should expect. We were going 0, and at time equals 1, we're going to go 1 meter per second. So it should we should have a little step function here, which is what we have. No surprises. Okay, it did solve. So what do you think the force is going to look like? It's not a trick. I mean, this is what it actually solved. I actually called MathWorks support about this because this doesn't make any sense. Tech support guy said, "Yep, that doesn't make any sense to me either." So apparently, it's a bug with their variable step solver. But it does kind of give us an interesting reason to try the local solver. So we'll click on use the local solver, and we'll just give it 1/10 of a second sample time. And we'll go back to this. You guys remember the delta function?
Integrated under that.
Yeah, energy under that curve is, total energy it takes to move that from a certain speed to a new certain speed.
So if you were to take the sample time and make it much, much less, that would be a lot taller than.
Yeah, let's do it real quick. Oops, what am I doing? Let's just do 1.
The solver time, is that the older one derivative to that backward Euler?
There's trapezoidal too. Don't be a snob.
I almost got beat up by a math instructor.
For calling it Euler?
Rosenhaus, you ever heard of Rosenhaus?
Yeah.
He used to be a boxer. I don't want to mess with him.
I've had some great philosophical conversations with him.
Yeah.
He-
No, he could keep you there for like 3 hours just talking about the most random, interesting things.
He told me I was brainwashed. Okay. So much taller, much skinnier Spike. I have strong opinions too, obviously.
Yeah.
But he's fun to talk to. Yeah.
I'm not quite seeing the correlation between the changing of the sampling time and what we're seeing.
Okay. So let's look at the quantity. It's like what, 23, 22 and a half, something like that, right? And this is at 1/100th of a second. So if I move back to 1/10 of a second, run it again. Now we're at 2.2.
So it's just spreading that step over the sample time.
Right.
And that's why it's step.
Because it's just energy flows that we're working with. So the solver, we're telling the solver how big of a step do you want to take. Yeah. So that's all good. And it's kind of messed with my slide sequence because it would have been nice to have it work the right way instead of having to point out a bug. But this is what we just did. This doesn't look right. And That's area equals the energy to accelerate. You guys know that stuff. Okay, so if we go back to not using a local solver, but instead using a fixed solver, you would think that would do the same thing, right? That it would say, oh, okay, this much energy under the curve, so blah, blah, blah. So let's do that, 0.1, and say run. So instead of running, it gives us an error. Not enough input derivatives were provided for one or more Simulink PS, blah, blah, blah. And this is exactly the same thing you were saying. The derivative of what we gave it was infinite. So it's saying, I don't know what to do with this because it's infinite. I can't compute that, so why don't you just hand me the derivative and I'll believe you, and I'll make it work. And you literally can do that. If you go right here, you can say input handling, provide input derivatives. And you can just hand it a derivative and say, just believe me, here's the derivative, and it'll go do what you want. And sometimes I've done that, but I wanted to show you a little more general way of doing it so that you can decide how stuff reacts. Because when you're modeling this stuff, you always have some time constant, some like, this is how much energy this thing can do, you know, because that's part of what you're capturing in the model. So let's talk about that for just a little bit. So what we're struggling here is the difference in sampling time and notions between discrete, like, or something that can change instantaneously, and a physical system where it has some kind of inertia, some kind of finite energy transition time. Like energy just doesn't go here to here, whereas like software, you know, the variable x is now 2, and at this instant it's 3, and it looks like a step function. And ultimately, for our project, we've got to connect these two dots, because we're going to be telling it, go to this elevation, go to this bearing, and there's going to be a hydraulic system saying, hey, wait, like I can't move that fast. Even if we try to slow down the steps, however small we make those steps, they're still steps, so we kind of have to solve the problem. So obviously on the sensing side, it's easy, right? We grab a physical quantity and push it into like effectively an A to D, and then that goes into software, and software doesn't really care. Like we grab that, but going the other direction from the D to A, that's kind of our challenge. Like now we're converting to a physical quantity, you know, and in the A to D, we're going from digital to analog. How does that work? Because the analog voltage, even though it's supposedly analogous in magnitude, is still a physical quantity. It's still a real energy that we have to cross that boundary with. So we kind of need some workhorse objects that are not real, which is kind of interesting to me because this is all about physical modeling. This is like, how do we model reality? So where do we go? Not reality, we go somewhere else. We go find these other workhorse objects. So transfer functions and rate limiters. And I'm sure you guys have talked about transfer functions and are sick of them, but there's some really good reason to talk about them. So just in case you don't remember, transfer function is a linear dynamic model of whatever. Usually has like a numerator and denominator, and it's in the S domain. Rate limiter, do you guys know? A rate limiter is just what it sounds like. It doesn't, it basically controls the first derivative of whatever the signal is doing. So our first derivative became infinite, so part of what we want to do there is make sure it doesn't go infinite, it has to go to a finite value. But when you stop and think about these two things, yeah, I want to talk about this next actually. These are doing almost the opposite to deal with the problem. So if you think about rate limiting or slew rate limiting, you're saying the first derivative can't be any higher than this and it can't be any lower than this. That's what rate limiting is. So what you're holding constant is the magnitude of change for a given time, right? Now think about in a transfer function, you talk about rise time, right, or settle time, or something like that. So instead of talking about the rate of change, you're just talking about the time of change. Okay? So they're fundamentally different. And you guys have probably talked about small signal characteristics versus large signal characteristics. And these solve, the rate limiting solves big signal characteristics. Because if you think about like a rise time of 1 millisecond, that might be great if you're going 1 volt. What if you're going a megavolt? And you can do that at 1 millisecond? That's a problem, right? On the other hand, what if you're going 1 millivolt? And you're limited by this, well, instead of being infinite, you're actually amplified by this rate limiter. It says it can go this fast, but it's doing such a small step that the time is super fast that it takes to, you follow what I'm saying? Like, so they're kind of mirror problems. So you can actually combine the two to solve a more general problem and say it's rate limited and it's rise time limited, and that way it makes it easy, makes it usable on the physical side. Sorry, everybody with me? So what I mean? Okay. Now, everybody seen this? I probably have, but canonical second order transfer functions. The main take home here is at the bottom, that form of omega n squared over s squared plus 2 zeta omega n s plus omega n squared. That form is super useful because it allows you to, if you say that this is a critically damped system, so zeta equals 1, that's this right here, it allows you to say, I want a smooth transition from this point to this point, and I'll tell you how fast in one parameter, one time constant. So we can talk about it in terms of omega n, which is approximately equal to 1 over the settling time. So it goes 2 pi radians per second in 1 over t settle. So you can see the zeta equals 1, critically damped, gets basically to 1 right at 2 pi. So this making sense? I mean, I'm kind of jumping into, I hope you've taken this class kind of stuff, but have you already taken this class?
I didn't write down, but yeah, we saw some research.
Okay. It also allows you to add some dynamics really easily and say, maybe it's underdamped. You know, maybe in this conversion, you want zeta to be a little less than 1, like 0.7 or 0.4, so that the transfer characteristics have a little oscillation. That might be what you want to capture, and that's a super easy way to do it. So what I did, and it's really easy to do, you just drag and drop the transfer function, put a mask over it, convert, you know, you could use both the damping ratio and the natural frequency together, or just use one. I just used the natural frequency and said it's going to be critically damped. And that way it's one of those workhorse blocks that you can just drop in and say, hey, I have no idea what my input's coming in as, but I know that this D to A can't move any faster than this. And so you can drag this and say the rise time isn't, you know, the time constant of the rise, you know what I'm saying, the time constant of the system isn't going to be any more than 1/100th of a second. So when you combine that with a rate limiter, and you can parameterize the rate limiter, then you get small signal and big signal characteristics, and it protects you from both. So that make sense? Is everybody with me why I'm saying this? Maybe it will help if you see an example. Or if you're all on board, I'll skip the example. Should I do the example? Yeah, okay. All right. So, let's see, that's the other one. All right, so here's our little mass system, and I'll call this MEC2. And where I'm talking about is the signal right here between the step and the converter. So I'm going to open these up just to save some time. And I call them bridges. So underneath this mask, there's a transfer function that's exactly like what we talked about, s squared plus 2, an implied zeta equals 1 in there, 2 times omega n, or natural frequency, in radians, plus omega n squared. So that's all that's inside. And I just parameterized it. I'll show you the mask real quick. Control M gets you into the mask. You pull in a time constant, and I said, okay, frequency equals 1 over the time constant, omega n equals the frequency times 2 pi. I just converted to radians. And then I put a mask on it to say, by the way, the time constant is such and such, so that you can actually see it. Because that's a really helpful thing to be able to see, in my opinion. So that way, when I change this to 2, you can see it on the mask. You don't have to look underneath the mask to go find it. So, if I hit run, this should take about 2 seconds to settle. It goes at 1 and gets there close to 3. Not exactly, but pretty close. Make sense?
Yeah, isn't it like that much for 99% or something?
Yeah, it depends on how you define t-settle. Yeah. I think it's 2 or 3% or something. The rate limiter block, you could just, I'll look under the block. There is something called a rate limiter, and you could just parameterize it directly, which is fine. I've done that, and but here I put in up and down parameters, and I masked it, and then I put on the mask so that I can see what those are. And I said, okay, in this case, it's 1 and minus 1. So minus 1 is greater than dy dt, which is greater than 1. And that way you can look at the block, and you're not having to look underneath, in the mask dialog box. So let's do this real quick. We'll just take one of them. Well, actually, I want to show you this. This is kind of interesting. So 1 to 1. And if we make a sine wave coming into this thing of magnitude 1, because the maximum speed of a sine wave that has a magnitude 1 is 1, because, right, derivative of sine is cosine and so on. But what if we make the magnitude just a little bit bigger, like 1.5, and run this again? It starts to shift the shape because it starts to look more like a triangle wave because you're limiting the rate. You can't really get to the acceleration you need to actually get there, and so it doesn't quite get where it would like to get. And you can see how it's starting to tweak with those things. So, and that just it's worth noting that rate limiters are nonlinear. Like we talked about last semester, that pretty much everything's nonlinear. It's hard to keep things perfectly linear. The second order transfer function is still linear, and that's why it's more popular, and you can use it for small signals. But okay, enough about that. Let's say we'll do this over 1 second, and just make enough room to drop this in. So here's our. I'm gonna go back to the local solver because maybe I can get away from it. I'll try it one more time. Variable step, everything's automatic, and I don't want to use the local solver. I think it's going to complain. Yep, it wants an input derivative. I don't want to give it one, so I'll use a local solver, and this time I'll give it a little more resolution, but it's not going to be a spike because I've distributed that signal, like energy transfer characteristics, over a second. So it gets up to 0.6 pounds or so. But all that energy is spread out over the 1 second transfer function, right? So I shaped the signal on the incoming side so that it made some kind of sense. Everybody with me? Okay. All right. Awesome. All right. So so those are those two things. That's what they look like unmasked. That's what they look like masked, which I already talked about. I just showed that. Okay, and we already talked about this a little, through and across variables. And I meant to take out those other quotes, that's okay. So electrical, voltage is across, current is through, mechanical, velocity is across, force is through, and hydraulic, so these are 3 domains we need to use. Pressure is across and flow is through. So when you think about variables, these kind of variables, they're measures of energy. And you need both because energy is going back and forth between kinetic and potential energy. So across variables are kind of a measurement of the potential energy of a component, and through variables are like kinetic energy of a component. So in your mind, I'm trying to tap into all the stuff you already know. You've already taken physics probably. You understand that you can really talk about most systems as energy systems and how it's trading energy between kinetic and potential. And so that's why that's why it's such a powerful concept, because you can talk about so many things as through and across. Yeah, I think we've killed that horse pretty well. All right, so hydraulics. Now, anybody done anything with hydraulics? I don't know, yeah, a little bit? Okay. With pneumatics or hydraulics? With air or fluid?
Just your normal old, I guess fluids.
They're probably hydraulics. If you jack up this car, they usually can hold more force than pneumatics.
Well, I mean, it wasn't air. So okay. I asked. So my brother's a classic car restoration guy. He has a shop here in town, and I didn't think about it until he mentioned it. But it seems like in the car world, people don't call it pneumatics; they call it hydraulics, no matter what you're using. That's why I asked. And he had airbags, so his was all pneumatics. And he still has a '62 Impala Super Sport that he like slammed down on the ground or stuff. It was kind of cool. But anyway, so hydraulics, I think, is interesting because growing up, I was around hydraulics growing up on a farm, and everything is hydraulically actuated, forklifts and heavy machinery. And then went to school and learned tons about electronics, and then one of the jobs after I graduated was hydraulic design. And so I think it's a really cool. It's complicated, but in a different way.
Yeah,
you know?
yeah. I used to work with hydraulics, like hydraulic pumps and hydraulic systems. Talking about like 75-gallon tanks with, a press that will distribute like 2,000 psi across a cylinder this big.
Right.
So,
Right. Tremendous amount of energy and force is going on, right?
Yeah, it's insane.
Yeah.
It's insane the amount of power you can transfer.
And it's so cool because it boils down to exactly the same thing as electronics. You're like, okay, well, and so when I started getting into this, and I was blessed to have some, some people around me that knew more about it, and so I could ask them stuff, and so in my head I was kind of like building this little Rosetta Stone of like, okay, so when I think about an amplifier, that's like this thing in hydraulics, and when I think about a resistor, an electrical circuit, because I do that stuff in my sleep, that's an orifice, which is just a restriction, of flow. Which, when we stop and think about that, it's really symbiotic to like, oh, that totally makes sense. A resistor is restricting flow of electrons, and an orifice restricts flow of the fluid. And so there's the physics are different, but the effects are the same. It causes a pressure differential. It causes a voltage differential. There can be an immediate, if there's no flow through a resistor of current, there's no potential difference. Just the same way in an orifice, if there's no fluid flow through it, there's no pressure difference. And it kind of just keeps going. And so it's really neat stuff. An accumulator is the same thing as a capacitor. Fluid mass, really, since itself has mass, is an inductor of a type. Pressure is voltage, flow is current. It keeps going on. And mechanically, you can draw these same analogies. So when you think about a mechanical circuit, you can talk about a mass being an inductor, you can talk about a capacitor being a spring, you can talk about a resistor being a damper. And so, I don't know what you guys had for mechanics, like for physics mechanics, but you guys had Rosenhaus, so probably drilled in, what's the solution to a second order, linear, ordinary differential equation, right? It's exponential. And it's any of them. And the thing is, like, so many things reduce to that, like when you start to throw away some of the nonlinear effects. And so when we're building these circuits, don't think about it like this, we're off in left field. Think about it like I have a foot in, I think everyone here is in electronics, so I know that stuff. All I'm doing is looking for a translation to be what's the equivalent, what's the analogy. So hydraulics, the way I think about it really is they're just bigger, slower, stronger versions. So if you want to go fast, you get small. If you want to be strong, you get big. And that's the trade-off. So we kind of have the rest of the time left to start making some systems and start to familiarize ourselves a little bit with the way these things work. So let's start with some electrical systems, and you can we can go off and do some other stuff if none of this stuff looks interesting to you guys. The things that I've done with Simscape have mostly been electrical, hydraulic, and mechanical, just because you're motivated to do what you have to do most of the time, and that's the stuff I needed to do. I had analog signal processing stuff, so I did that with op amps, and so I did the modeling for that using Simscape and made models of whatever fidelity I needed of those op amps. Some of it was SPICE models, some of it was less complicated ones. And I made amplifiers and different circuits and multipliers, and so I thought we could do a little bit of that and hop online, and it's like cookbooks of like I want an analog signal processor that does this. Okay, which op amp configuration do we need? And getting to know some of that stuff, like what is the effect of a particular input impedance or an output impedance, and how does that affect our overall voltage bias and all that kind of stuff. It's a great place to play because it's so fast to try something new. So on the hydraulic side, there's two major classes of actuators. There's cylinders, like I'm sure you guys know what that is. Hydraulic cylinder is like a linear actuator, and a motor is a rotary actuator. And so we can make some systems with valves that control those, and that's going to be our main driving force to actuate the turret and set it up. So I think we'll start there, and then we'll do one, and then you guys can we'll go to the thing you guys think is most interesting. So let's do the motor. So solver. I'm going to pull up the library just so you can see this stuff. So hydraulic reference looks a heck of a lot like a ground. That's basically the tank. A motor, we actually need sim hydraulics for that. So we'll go down here into fluids, isothermal, because we don't really care about thermal effects right now. So we want pumps and motors, and we will just use a fixed displacement pump. And then we need a valve, a directional valve. So valves are one of those things like science in and of itself. There's so many different kinds of valves. And the main advice I can give to you is don't get intimidated. Just look at them a little while. They're complicated, simple things. And we'll talk about why. But anyway, what we need is a valve that will let us, that one will work. Okay, so let's talk about this valve symbology here for just a second. So it has 3 positions and 4 ports. And so think about this as if, let me draw, let's see, constant. Sorry. Okay. I'm just using this as something to cover things up. So, all right. So the way spool valves work is you have a spool with cuts in it, and you shift the spool so the different cuts line up with different ports. And so when you look at the just make this bigger so we can see it better. When you look at these symbols, you think first about the position of the spool. So if the spool is centered, then what this does is the pressure port gets connected to the tank port. P goes to T, and A port is blocked and B port is blocked. So when the spool's centered, right in the center here, nothing happens because it's just like a flow through, and the thing it's controlling is blocked. But when you shift and you go to this position on the left, then pressure, the P port here, gets connected to A, and the B port gets connected to tank. So that turns things in one direction. And then when you shift the other direction, it reverses that. Does that make sense? It's straightforward.
I've always wondered that for the longest time, because without an explanation, it's confusing as fuck.
It is.
It makes absolute, but that makes perfect sense.
Yeah, and it's one of those, like, how deep does the rabbit hole go? Because what about transition regions, and how do you like shape the geometry of, we're not going to get into that, but just on a basic level, it's not that bad, right? Like it's just connecting dots, just in the same way like someone says, oh, electronics isn't that complicated. Well, you go take electronics. Electronics do, and all this other stuff with semiconductors. Like it is. But how often when you're thinking about a circuit, you kind of say, Ohm's law, blah blah blah, and a lot of the thinking is kind of governed by the first principles, like, okay, well, I have about this much voltage and current's going through here, and, right? I don't know if you're like me. Maybe I'm just more simple-minded, but I'm not thinking about all of the biasing of the semiconductor material and the diode and how it breaks down. Like, maybe that's because I'm not spending my day on that all the time. But anyway, so what we're going to do is start to connect these things here. The S is the spool position. So you can see it's got that like open triangle physical signal. So we're going to connect the pressure port to the pressure port, and we'll actually connect this to tank. I'm going to hide these things. Format. Okay. So we'll pull out of the tank. It goes through a pump. It goes out of the tank ports connected to the tank on this. Okay, now we have most of the circuit, but we still need a motor. So we'll go back over here to pumps and motors, and we'll get a hydraulic motor, fixed displacement. Connect A to A, B to B. Okay. One of the interesting things I think about hydraulic modeling is that you can't really do it in one domain like the way you can with electronics, because you really need to connect loads to it, and the loads are mechanical, and you need to drive it with something, and you're driving it with a mechanical, like spinning a shaft to turn a pump. So I think that makes it kind of an interesting thing, because you can't only do it by itself. So we don't want to get crazy. We could actually. It's really neat. I realize I'm a geek, but I spent a day one time modeling a diesel engine, figuring out how to like balance the torque speed curves, because it's just feedback loops, right? of, hey, I'm supposed to go 1200 RPM, but I have this torque load, so does it droop? How does that work? And then I realized, oh man, there's a block. I could have just drag and drop, but I learned a lot, so I was okay with it. So we're not going to get into that. We'll just we already used a constant velocity, so we'll use that. That's a mechanical source, an ideal angular velocity source. Some of it's just getting used to what they call things. So connect that up, and we need a rotational reference. So here's the ground for that. And we need a PS to Simulink. And we need a Simulink to PS. Okay.
Have you ever applied to MathWorks?
No, I haven't. Thought about it.
You'd probably be very happy there.
Well, maybe. I don't know. Nothing against them. I always have other ideas, you know what I mean? Hard to nail me down and work on one thing for very long. But, yeah.
I worked there for a couple of years and then do something else.
Yeah.
That's what I do. Pretty much.
Okay, so this signal, we're going to, most of the time you talk about RPM, right? So we'll just put a constant, and nice diesel engine RPM is about 1600. Turn on, whoops, turn on port units. What?
I think there's some big like boat engines, those massive freighters that are like 10 RPM or something insane. They're insanely efficient too. Probably burn a bunch of bunker fuel and pollute the ocean.
So you're an optimist then.
People have read into bunker fuel. You should read about the crap they're allowed to burn on the high seas. It's disgusting.
I imagine it is. No one wants to burn it on the land, so.
Yeah, exactly. It's not like we get food from the sea or anything like that.
Well, I'm going to focus so that we can finish, but it's an interesting conversation. Okay, so format. Okay, so that's coming in. We're spinning this thing at 1600 RPM. We need to tell this a few of its parameters, like displacement. Just take my word for this, 75 cc is good enough. So 75 cubic centimeters per revolution. And we'll make our volumetric efficiency, basically how efficient at a given pressure we can push all of the fluid out, and nothing's 100% efficient because there's leakage around all the mechanical elements. So we'll make the total efficiency, so that's volumetric plus mechanical, we'll make that, or times mechanical, make that 0.8. The rest of the stuff we can just leave, because it has to do with stuff that we don't care about.
Volumetric efficiency means stuff kind of stretches when you apply massive pressure, or
No, it means that you are, think of it like a cylinder, like if you have a cylinder that you're using like a pump, right? And maybe you're pushing through something that requires 1,000 pounds of pressure, right? And so you're getting some flow out, and you're pushing this other cylinder, right, with this, but some of that oil leaks around the piston. And so this is saying 10% of it will leak around the piston, which is actually not bad as far as, for piston pumps. But things like gear pumps are like 75%. So, like as far as efficiency, that's why electric stuff is so much better, because you have all these mechanical losses from friction and these volumetric efficiency losses. But the problem that I've run into in thinking about projects like, oh, I really want to do this and get this, I can't get the power density out to where I need it, with an electrical thing, or it's not rugged enough because it can't stand up to the vibration. Because I think I told you guys one time, a lot of my work is like with tree shakers, so it's like 20 G's at 35 hertz. Well, maybe 30,000 pounds of force out the trunk, and I can't get an electric motor to live. But maybe they're there, maybe they're coming. But what's that?
thorium.
Can't hear you.
A thorium reactor?
I don't know what that is. Are we talking about science fiction now? So anyway, so here we have this. Now we need to control this little this spool position. So the way we do that, I just clicked on the valve here, and again it's like that first day when I had the don't panic slide. There's a lot of stuff, but just relax and think about it. It's you know, when you get I remember the first time I looked at a electronic device like an IC data sheet, and there was like 4 pages. I'm like, geez, this is complex. But really, right? Like, well, you know, but I mean like the actual data sheet, the part you care about, you know?
Yeah.
And is it your experience too, like you really end up looking at a couple of the things that matter for a certain project, and the rest of it's like, I don't care what the parasitic capacitance is, it doesn't matter for me. Some of this is that way also. So like flow discharge coefficient, critical Reynolds number, that's beyond the scope of what we care about. For us, we want our maximum passage area, which is what the cross-sectional area of the hole that's going to open on the valve. So let's just parameterize it kind of explicitly here, and we'll say this is, we'll talk about it in terms of a diameter in inches, because that's how I think. And we'll say it's going to have 1-inch ports, and cross-sectional area of a circle is diameter divided by 2, which is the radius squared times pi. So that's that's a quick way to just parameterize it and say I want 1-inch ports. And my valve maximum opening, this is the stroke of the spool moving back and forth. So the linear, right now it's set at 5 centimeters. These things barely move, just a little tiny bit, and then those, I call them lands, I think, line up with the ports. So that's fine, we'll just leave it at 5 centimeters. Everything else, you can set some leakage stuff and initial things. That's all good. So now we need another one of these guys. And this time we'll talk about it in terms of centimeters. Whoops, yeah. So now we're going to control the valve with something. And why don't we, probably going to regret putting a step function here, but let's do it anyway.
So is it gonna, it's looking for a value from 0 to 5 centimeters?
From -5 to 5. So center position is 0. You can shift one way or shift the other way. So
What happens if you're somewhere in the middle? Like 2?
you mean like between 0 and -5 or something?
Right, if you're at 2 centimeters, let's say that's the position. Because, you know, it's clearly not at one of the...
Right. You can think of it as, well, what's partway between fully closed and fully open?
Right.
Partially open?
Does that model it?
Yeah. Yeah, and some of it, and this is where this is where it gets, you can dig down deep into the rabbit hole, because you can model your own valve, and all it is really changing orifice sizes for a particular position. It's not rocket science, but you can make it do whatever you want.
Right.
And all of that, like as far as valve design, just goes back with how they make the spool and how they make the ports. So it's really neat, because you can capture, hey, I know my spool weighs this much, and I know my spring constants centering the spool are this much, and you can figure out what your natural frequencies of the spool are that would mess you up. We can, really dig in, and that's this whole balance. The first day we talked about fidelity versus efficiency of modeling. You can dig way down if you care about it, and I'm hoping we can get away with not doing that for this, just because of time. So this is going at 1, it'll go from 0 to 1. Let's put it at 5. What?
Oh, yeah. It's 6.
Oh.
Go to the side of that.
I think it saturates. But again, I mean, we could make it so something else happens. Just yeah. Then it causes a leak and it opens a hole, and yeah, you could model it. Okay, so I'm gonna cheat here a little bit. I'm gonna go to the Simulink to PS converter and look at input handling, and filter input with second order filtering, and look what it has, a time constant. So this is the same second order canonical transfer function, unit gain, critical, yeah, it's built in. The reason I think it's better to actually use your own because you can see it explicitly there. You don't have to dig in and look for it. And oh, whoops, I forgot that I had second order filtering. Because once you build the model, after a while, you don't look at every parameter of every component. And so I kind of feel like it makes more sense when you're doing something longer term to invest that little bit of time and use an explicit block. But because we're low on time here, I'm going to say this can move as fast as 1/20th of a second. And that's all I want to do. So that's in centimeters, that's good. Okay, so all this stuff is all good now. Now we just need a load. So we just need inertia. And this is the rotational equivalent of a mass, the same thing as an inductor, right? So we're just going to give it something to struggle against. And then we should probably say how big this thing is. So let's pretend, yeah, I don't think it's slugs. That's a funny unit, right? At one point I knew speed of light in furlongs per fortnight. I was going to screw with the professor and put that into my solution, but I was nervous about the test, so I was like, nah, forget it. You do the conversion. But, okay, so I'm going to put this at 5,000 pound mass times inch squared, just because that's a unit I am familiar with, so take my word for it. It's something about this big around, like a pie slice. It'll have a good inertia, so it won't start up too fast. 5,000 pound inches squared. Okay, so that's how much that is. We already set the displacement. No, we didn't. So I'm going to make this a little bit bigger, 120 cc's. So you remember the pump was 75. So this we're making 120, so we're actually gearing down hydraulically, which is kind of cool. You can mix and match those displacements and do dynamic gearing. This is all fixed, but all right, and the last thing we need to do is measure this. So we need a rotational sensor of some kind, motion sensor. Connect U to U. We need a reference point because this is an across variable. We need to convert that, and we don't care about acceleration. We care about, or angle, we care about velocity or omega, W. I'll put a scope here. I also kind of care about the pressure. So I'm going to put a, pressure sensor. And I care about what the pressure is right after the pump. And I need a reference tank for my pressure. Oh, I want to ask what the speed is in RPM. I want to ask what the pressure is in pounds per square inch, PSI. And I'll put that back to a scope. Okay. So think for how many different components we have going on here, how many equations this would be. I think this is kind of cool if we look at the statistics viewer. It'll tell us there are 78 variables here. We did this in like 15 minutes. Some big time savings. Okay, so I'm not sure if this is going to work okay, but we'll give it a shot. Let's watch the pressure first. Look at that. So we shot up to 12,000 psi, which would be pretty high pressure for most hydraulic systems. And it took us about a second to get this thing going. So here's we went up to 1,000 RPM, which makes sense because we were driving it at 1,600. Okay, so let's just add one more valve that you'd normally put in a hydraulic system, and then this would get really hard to model in a linear kind of way. So we'll add a pressure relief valve because we know that's too much pressure. So we'll go down to hydraulic valves, pressure control valves, pressure relief valve. And they have really cool symbols. Don't let it scare you that they're not that complicated. Just it's like electronics, you know. They have really sophisticated symbols sometimes, and they really come down to what's going on, how you use it. It doesn't end up being so bad. So again, there's a good number of parameters, but the stuff we care about is maximum passage area, and we'll give this. How about we give this a lot of room? So we'll make it a 2-inch diameter, squared times pi, and it will open at 3,000 psi. So that's our maximum pressure. TS. And the rest of this stuff's okay. All right. So now that that's in place, we shouldn't have this spike. We should have, like, we get up to pressure and it holds the pressure for a while, and once we get to our final speed it should go down. But we shouldn't be able to get there as fast now because we don't have the pressure to hold it, like the acceleration. Aha, right? And now it takes us closer to 1.5 seconds to really get going. So that actually worked out kind of good timing wise. I'm kind of curious, we were at 78. How many parameters do we have going on now? 85 now. So no problem. So that's pretty good work for 20 minutes, I think. And this is basically, this circuit, in essence, is what we're going to use to control the turret. And we're going to connect it up through a gearbox because we've got so much mass to turn around. But we're going to have a gearbox, and we're going to have a big, huge pump and a big, huge motor, and we'll figure out, we can plug into this and say, hey, this is how much energy, how much horsepower it would take. So this is where we're going to go next week. So.
It's funny you keep